Welcome everybody to this new lecture of the series Big Data for Engineers. What's on the menu today? Well, first we are going to finish this part about data modeling, and then we'll start processing data massively in parallel and in batches. So, okay, so what have we done last time? We have seen that JSON and XML, the formats, you can parse text. This is actually text that can be parsed as JSON or XML. And when you parse it, you can actually draw this as a tree. So this was the most important part of the data modeling for XML and JSON. These are trees. And we saw that collections of trees are nothing else than denormalized tables, right? And I will come back to that at the end of this part when I will speak about data frames, because we will see why trees are actually like denormalized tables. But before we do that, in order to stick the data into data frames, we first need to validate it, because if we don't validate it, it's such a mess that it will not fit in data frames. So this is the technology stack. We already covered this, and now we are at the data modeling and validation stage. So we saw that that's the visual of what I said. When you have a document like that, you can represent it as a tree. So the idea is that if you just dump JSON documents on HDFS or on S3, you can actually make it a big mess, because you can just dump any document you'd like, and there is no structure or no order in there, right? So if you don't have any schema, by default, it's going to be quite heterogeneous. And this is fine, because sometimes this is how the data is, it's messy and so on, right? You need to clean it up. But after you have cleaned it up, the data will be more homogeneous in the sense that there is some structure. You will have the same keys in all the objects, the same elements in all XML documents. Maybe some key is always going to be a date, another key is always going to be an integer, and so on. So this is how you get some homogeneity, and this is when we will be able to fit that in a data frame. So this is what happens when you have a schema. You can validate that the data indeed follows that structure, that very regular structure. So remember where we were last time. Before I show you the schemas and what they look like, I wanted to cover the type system for validation. What is the type system? Well, it's all the possible types that you can have in your JSON and XML documents. I present to you the types. I presented to you the types in a very generic way that is not specific to XML or specific to JSON or specific to any schema language. It's very generic. If you use one tool or another tool, they might have a bit of differences and not have exactly the same types, and have a, it's not exactly the same everywhere. But I want to equip you with generic knowledge about the type systems, such that when you want to learn a new tool or a new schema language, it will be easy, because you will notice it's just the same types all over, right? So this is why I started with atomic types. This is everything that is either text in XML or the atomic values in JSON, right? So in XML, there's only text, right? But in JSON, there are strings, numbers, Booleans, nulls, right? So this is what I started with. So I already told you that first you can have strings. That's the most generic thing you can have. A string is just, some quoted sequence of characters. Foo, Zurich, Isabelle Alstenar, that's actually known literature. Then I told you, okay, there are numbers. There are actually 3 kinds of types for numbers when you want to validate it. It's not something that is so obvious in JSON, because in JSON, there's just numbers, right? And that's it. There are just numbers that can have digits, that can have dots, and that can have exponents. In XML, there's absolutely nothing. There's, again, just text. But if you want to validate, then you need to specify type. So what types do we have? Well, if you know a bit of Python or Java, you will not be surprised, because as I told you last time, first you have the integers. And here you have various intervals of integers, right? So you have small integers, larger integers, even larger integers, and extremely large integers, right? So these are the first ones. So typically in Java, it's called byte, short, int, long. But again, it depends on the language, right? I think in Python, you even have int, but int has actually no limit, I think last time I checked. So you see, but in most programming languages, this is limited in the size. So you can only have a specific interval of integer every time. So that's the first type. The second type is arbitrary precision decimals. It's when you have text like that you want to validate as a decimal number. It's just a sequence of digits with a decimal period in the middle, right? And that can be arbitrarily large. There is absolutely no limit. These are the decimal numbers. I think in Python, it's called float, this one. There are plenty of names in XML or JSON. It's rather called decimal. In SQL as well, I think it's called numeric or decimal. So you see, there's plenty of names, but basically you can have arbitrary precision decimals. That's the second kind of number type that you can have. And the third kind of number that you can have is approximation of real numbers. It's whenever you want to do very efficient computations. There are two types that you find in many languages that are called float and double, in Java and C++, for example. What is that? Well, it's just real numbers, but approximated to a precision of 7 digits, like this. This is if you encode it on 32 bits, so you have 7 digits of precision, but it's floating point, right? So it can be with plenty of zeros behind or plenty of zeros in front, but you can store 7 digits of precision. If you go for the double size, then you can store with 15 digits of precision. And again, it's floating. So you can have the decimal period anywhere you want with plenty of zeros here or plenty of zeros there, but 15 digits approximately of precision. So why would you use these ones rather than these ones? Well, this is because this can be very inefficient to compute on many computers, whereas these types here, float and double, they are a standard, and most of the CPUs on modern computers are very, very, very good at computing with these formats right there. So this is why also in XML and JSON and in big data, we like to sometimes type the numbers in that way that can be stored with 7 or 15 digits of precision efficiently. And you have, of course, an interval of the powers of 10, right? So this is how you shift, that's what I told you, the floating point. This is how you can shift the decimal period, right? Powers of 10. All right, think of it as the scientific notation, if you want. It's basically a mantissa times a power of 10. Okay, so these are numbers, integers, arbitrary precision decimals, or these approximation of real numbers, float and double. All right, then we have Booleans. Okay, Boolean is easy. It's true or it's false. It's just two possible values. And you'll find plenty of representations, yes, no, true, false, TF, and so on, 1, 0. But anyway, in terms of value, it's basically either it's true or it's false. That's called the Boolean. Okay, then we have dates and times. That's also very important, right? Dates and times. So we can store dates, we can store times, we can store timestamps that are basically the date plus the time specific point in time, or durations. Okay, let me go through them. A date is a year and a month and a day, if you use the Gregorian calendar, right? So that's basically what a date is, right? A time is basically the hours, the minutes, and the seconds, but potentially with the microseconds or milliseconds, right? And again, that depends then on the schema and the specific type system, but most of them allow you to do that sort of things, right? And finally, the timestamps is everything. You have a year, a month, a day, a time in the day, in hours, in minutes, and in seconds, all the way very often to the microseconds, right? Right? So this is, why is that a timestamp? Because if I tell you exactly that, this is a specific point in time, right? This is why. What I didn't say, to simplify, is that there's usually also support for time zones. So typically you're going to say it's GMT, it's Zurich time, and so on and so on, right? I just simplified here by not talking about time zones. All right? Okay. Then we have time intervals. So what is a time interval? For example, 1 hour is an interval, or 2 days and 4 hours is an interval. So these are all the possible combinations that you can have, right? You can have like 2 years, or 1 year and 4 months, or 5 months, or 2 days, or 3 days and 4 hours, or here you can have 2 days, 4 hours, 3 minutes and 20 seconds, and so on and so on. So these are all the combinations, right, that you can have for durations. Why is there this black line right there? Well, it's because what if I tell you 1 month and 2 days? That's ambiguous, right? Because is it February or is it March? If I tell you 1 month and 2 days, but it was February, then that's 28 days plus 2 days. But if it was the March, then 1 month and 2 days is 31 plus 2 days, right? So this is why we avoid, in general, mixing months and days, because of this ambiguity in the number of days that there is in a month, right? But this is the only little difficulty right there. Apart from that, you can have any intervals. All right. The next type is a binary. What is a binary basically a binary representation, imagine what you want to store is a picture or a video or audio, you know, or whatever file you want to store in there. You know that in the end, it's zeros and ones on a machine. Well, it turns out you can also store a picture in JSON or in XML, right? And of course, it's going to be represented with some specific, for example, a hexadecimal representation where you express the binary in base 16. But basically, this is supported. So there's a hexadecimal representation, and there is a very smart encoding that is called base 64 that is able to encode pictures as letters and digits and a few more signs. So it's actually brilliant. I'm not annoying you with that. I'm just saying that it exists, and you can actually store pictures and audio and video in JSON or in XML. It will just look like text. Okay, and then finally, null that we saw in JSON, it's a special value that is basically, that says, okay, either we don't know, or we couldn't compute it, or you're not authorized to see it, or it doesn't exist, and so on. So that's null. Okay, that's the atomic types, right? What is specific about atomic types? It's the fact that everything that I talked right here are abstractions. A date is an abstraction, a Boolean is an abstraction, a number is an abstraction, right? It's what our ancestors came up with in the past millennia. But as you know, all of these abstractions, dates, numbers, and so on, they can be represented as text, right? And in particular, you know that a number, the concept of a number, which is in fact to count things, right? You can represent it in a decimal form, for example. For example, the number 100 can be written as 100. That's a decimal representation, right? So you have to distinguish for these atomic types the notion of lexical space, which is what does it look like in text when you have an actual XML document or a JSON document and you actually write it as characters, versus the mathematical abstraction of the value, right? So you have another example is 4 or plus 4 times 10 to the power of 0 or 100 in binary. These are all representations of the number 4. So the mathematical concept of 4, in that case, 4 oranges, as a cardinality. But the representations as text, there's plenty of them. So you have to understand the notion that when you store it on HDFS as a JSON document, it's going to be text looking like that. But from the moment you parse it and you validate it and you start processing it, you are working with the mathematical abstraction of the number 4. And that is the power of data independence, because you don't have to worry about the representation anymore. You're working with the concept of 4. And then you have addition, subtraction, and so on. You can start manipulating it. All right. Another aspect that many validation systems have is the notion of the subtypes. A type is actually nothing but a set of values. For example, the type integer just corresponds to the set of all integers. The type date corresponds to the set of all possible dates, right? The type Boolean is the set that has true and that has false. So these are sets in the end, the set of acceptable values in a type. And I'm thinking of sets of these, of the abstractions. So then you can define subtypes. Here's an example of subtypes. The integer type is a subtype of the type decimal, because all integers are in particular decimals. They are just decimals that don't have anything after the decimal period, right? So integer is a subtype of decimal. So if it's done well, then the value space of the subtype, in that case, the set of all integers, is a subset of the value space of the supertype, in that case, all decimals, right? Okay, so this is something that is almost common to all systems. Okay, this is about atomic types that I have been speaking so far, right? So strings, numbers, dates, and so on. This is everything you can have as text. And I told you that in XML, in JSON, and in many other systems, there is also the structured types. In JSON, that's objects and arrays, right? Objects and arrays. In XML, that's the notion of elements or of attributes. We will see that in data frames, we also have the concept of structs, of array, and so on. Computer scientists like to think of that on a very high level of abstraction, just like mathematicians. So what is in essence a JSON object? Well, this is a map. It's a key value model, right? This is an object. Why? Because it associates keys to values, right? That's what an object is. The other one that is associated to arrays, the abstract name for that is list. An array is a list of values, right? you think of that. It's an ordered list of values. So this is the very high level theoretical name, map, list. And then depending on the actual model or technology you're using, you might not actually say map or list, but you're going to say object and array, or the set of all XML attributes, or an element, and so on and so on. What's important is to realize that this is very similar. If you look at a JSON object, or if you look at the set of XML attributes associated with an element, it's all a key value model. A JSON array, an XML element, it's just a list of its children, right? So these are all lists, all right? So if you see that, then you have this high level perspective on things, right? So maps and lists on a very, very high level. And this is what is taught in computer science curricula, in algorithms and data structures lectures. We teach that there is maps, there is lists, there are also others that we don't really use there, that are sets, for example. And these are the mathematical abstraction of these things, called abstract data types. Okay. Okay. So these are the structured types as opposed to atomic types. Then one more thing that many type systems have in common is the notion of cardinality. Why? Because we are in a big data lecture. If you use Python or Java and so on, you manipulate one value at a time, right? But in big data, you can be touching billions of values at the same time. So you are looking at sequences of values, sequences of records, sequences of trees, sequences of objects, very large sequences. And then you can restrict the size of these sequences. For example, you can have a sequence of size 1 or a sequence of size 0 or more, meaning anything. You can have 0 or 1, either empty or one item, or 1 or more, right? Meaning it cannot be empty. Well, computer scientists typically associate these signs with this. So star means any number, the question mark means 0 or 1, and the plus means 1 or more. I don't really know why. This is how historically computer scientists have come to make this association, right, between the size. This is very, very common to make this association. And you might also see some keywords depending on the technology, like repeated if it's 0 or more, optional if it's 0 or 1, and so on. Okay. And in order to show you that this is really universal, what I have told you about the type system, and yet at the same time there can be variations, I'm showing here a table. It's actually one of your predecessors in a class, I think 1 year ago, who asked me that. Can we have a comparison tables of the types across several systems? So this is what I prepared, and this is what you see here. So you see here there is the JSON schema. We'll look at it a bit later today. JSON, XML schema, Spark SQL. We'll also look at it during the lecture. PostgreSQL, Python, and so on. So I basically listed a few types and I put them in correspondence with each other. And what I'm saying here is if you learn one of these, let's say you learn XML schema, then you've learned them all, right? Because if you realize that you know what a double is, this standard of floating point that I told you earlier with 15 digits of precision, well, it's called double in JSON, it's called number in JSON schema, it's called double type in Spark SQL, it's called double precision in PostgreSQL, and it's called float. I don't know why it's called float, but it's called float in Python. So you can see this correspondence table. What I want you to realize here is, you might be thinking, oh my God, this is so big, I have to learn all of that by heart. No, that's not how it works. What I want you to realize by seeing that is that it's really the same everywhere. It's the same everywhere. It's just that people can call them differently. It's exactly like in Switzerland. We have as many dialects as villages, and at some location people say Zündhölzli, at some other location maybe Allumette, and so on. But we all understand each other, right? And if you have learned one of the dialects in one village, it's very easy to actually understand people from other villages. So look at that like Swiss dialects, like Swiss German dialects, and there is just some sort of correspondence, and everybody can understand each other, right? Okay, so this is just for future reference that you can actually use this correspondence table if you want to. All right. Any questions on the generic knowledge that I've told you about types, atomic or structured? Any questions so far? Is everything clear? No questions, Wenshi? Also in the lecture hall?
No, not yet.
All right. So I'm assuming it's clear. All right. And maybe for many of you, if you already know how to program in Python or in Java or in C++, you already knew that, right? Because you've already been exposed to the type systems of these programming languages, right? So maybe it was little effort. For those of you who maybe didn't program so much, maybe that was a bit more to actually learn, but yeah. All right, okay. Then let's go ahead now and apply all of that to actual validation of first JSON, and then we'll look into Excel. All right, so let's look at JSON schema. JSON schema allows you to specify the structure and constrain the structure of a JSON document. For example, this is a JSON document, very simple. It's an object. It has a key name associated with the value Einstein. What if I want to validate that it satisfies the schema? For example, my schema could say that name must be a string. I need an object with a key called name and with any value that is a string. So I can actually do that, and this is what JSON schema, this is one of the schema languages does. You basically can define a schema like that, that says, okay, I want an object, and the properties, it's another name for keys. As I said, Swiss German dialects, right? Properties, keys, it's just like split, sharp, chunk, block. There are many words for the same thing, right? All right, so the properties can be name, and name must have the type string. You notice that this is actually JSON itself. So you are using JSON in order to describe JSON. There's a beauty in that, right? But you see what's going on here. We are saying we have an object with a key called name associated to some string. Right? This is just paperwork. It's like filling your taxes. It's just saying that, okay, this is a JSON schema, and this is this version of JSON schema, and blah, 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 blah. You don't need to pay much attention to that. But now I'm going to give you a few examples, right? So you can associate when you are so this is the schema itself. This is the original object that we want to validate. And you can associate it with some schema in that way with the $schema, schema.json. Okay, but this is not the most important. The most important is this. It's the few examples that I'm going to give you. Now I'm dropping all of these dollars and blue things because I just want to get rid of that distraction. And I'm just going to focus on the actual validation, right? So every time on every example I'm going to show you, there will be the JSON document that we want to validate. And here there will be the schema itself, right? And do not be surprised, again, the schema is itself in JSON, right? But this is a schema. So this is why I wrote here that's a schema, and that's the instance. So the instance just means that's the document we want to validate. Okay, so here we have an object. Yes, that's an object. We have the property name. Yes, we have the property name, and name has the type string. Yes, this is a string, right? Double quotes and text inside. Okay, here's another one. Now we have an object. Yes, that's an object. We have two properties, name and first. Name and first, yes, that's valid. Name must be a string. Yes, it's a string. And first must be a string. Yes, it's a string. Do you see the logic of that? It's really just a description of the expectations that we have about the structure of the document. By default, properties are optional, meaning that if I say first is of type string, it's okay if it's missing. It's absolutely okay. If it were there, it would have to be a string, but if it's not there, that's fine. So this is fine. This is absolutely fine. And here, this document is valid against that schema. If you want to restrict in the sense that you do want first to be there and you don't want to allow that it can be missing, then all you need to do in your schema is add required here and say, okay, I require name and first. So you say, okay, name must appear. Yes, it appears here. First must appear. Yes, it appears here. And they are string and string, string and string. So that's all good, right? See the logic? It's also fine to have extra fields, right? So here I said there's property name and first, and here I have age that is not mentioned anywhere here, but this is fine. It's just that then you don't check. Age can be pretty much anything. You don't really care because there is no constraint about the age right there. In that case, it's an integer, but it could have been pretty much anything. And again, if you do not want that, if you don't want to allow that sort of things, all you need to do is say additional properties false, and that will take care of forbidding anything else than this to appear in there. Do we have a question?
Yes. If property first is missing, Does it mean that when we parse it, it will be filled with null?
That's a very good question. This is the notion of what you are asking is not validation, it's annotation. It's the fact that you can modify the instance in order to make it fit somewhere. Some schema languages allow you to do that sort of things, meaning that they will autocomplete your documents with first, and you can also specify a default value, right? You can say, okay, if first is not there, then just fill it with, I don't know, Gödel, right? Let's talk about completeness, right? So some schema languages, I don't remember for JSON schema, right? But there are schema languages that allow you to do that, to automatically extend and annotate and you know, add stuff in the instance to make it fit in the way you want. Yeah. Okay. All right. Then you can also say type number here. There's only, actually, it's not a very rich type system in the case of JSON schema. You can just say number, just like JSON, and then it will check that this is a number. Then you can say it's a Boolean, then that's true. You can say it's null, then that checks that it's null. You can have also any value. So if you just put this in their location with anything, then in that case, it's an array. You can also say location true. There are several ways of doing that. Then it's going to allow for anything, and so on. You also have the possibility to have union, meaning that you can say that the property name is one of string or number. So here it's a string, so that's fine. Any of, I don't really know the difference between the two. If it's synonyms, maybe there's something subtle, but basically it's the same idea. Or all of. If you want it to be at the same time an integer and a number, then that's what it's going to be doing, right? Okay. You can also specify unions in that way. So you see, JSON schema can be a bit verbose, right? There's a lot of options or a lot of ways to actually do things. You can forbid a field. You can basically say you can allow anything. You can have extra fields, but not location. So if you want to forbid location, you say location false, then it will make sure that it doesn't appear in there. All right. Then you also have more restrictions. You can say, okay, longitude must be at the very minimum minus 180 and at the very maximum 180. And then it's going to check that it's within the interval, right? So in essence, this is a subtype of number, right? That is in these bounds. All right. You can say that you want an array. So R is an array. That's fine. It's an array. You can say that it's an array of integers, right? By saying type array and items of type integers. So now you have an array of integers, right? And so on. So this is basically just a 101 of JSON schema, right? This is what it looks like. Now, I threw a lot at you, right? I probably threw 10 examples at you, and I'm pretty sure it's not something that you already know by heart, or you know, you might be confused or think it's hard to learn. Don't worry. There will be exercises. So the TAs have prepared exercises for you with concrete examples and instances and so on and schemas. And then you can also look up the documentation of JSON schema if you want to learn it a bit. So you will have exercises, do not worry, right? But at least I hope that I could give you the appetizer, you know, and give you a taste of what validation looks like and what a validation language looks like. And in particular now, you know what it lets you do. Right, so you can check the types, you can allow or not allow extra values, you can make it optional, you can make it required, and so on and so on. All right? Okay. Now, let's go into another schema language. This one was designed for pedagogical reasons because it's much simpler than JSON schema. It's called JSON, right? And so now I've introduced it in the lecture, I think, last year, and now we have implementations, we have a validation page, so this is growing in importance. It's really because pedagogically it's easier. For example, this is the instance and this is the schema, right? So you can see it's much simpler than JSON schema. So we say name is a string. We can say name is a string, first is a string, and that's the instance. We can say first is a string, by default it's optional, just like in JSON schema. So this is valid against that schema, but you can require them by adding these exclamation marks right there. Right? So if you have an exclamation mark, you require that name must exist and first must exist, right? Then extra fields are forbidden by default. We will see later it has to do with the fact that we want to build data frames out of them. And you can have numbers with the types integer and so on, 142. So now you're going to ask me, okay, what types can I put in there? Well, that's easy. That's the slide that I showed you earlier. Let me rewind a bit. There you go. This is everything you can use. You see all the types in there, and it might not have escaped your attention that this is pretty much the same as in there, right? So if you learn one, you basically learn the other. Okay, but let me come back. So this is the menu basically from which you can pick your type. So let me go back. Okay, so you pick from the menu, and everything from the menu you can basically put in there, right? To specify what you allow and what you disallow. So there's Boolean in that case, there's null for nulls. You can say item, that's the most generic one to allow for anything. You can have array that basically allows for an array of anything. Alternatively, you can say an array of items, right? It's just the same thing. You can say an array of integers, you see, and that's what it does. So you see, this is much more compact than JSON schema. In JSON schema, it was much more verbose, right? But here, this is JSON. This is very compact. You're just saying we have an object that has a key R that is an array of integers. And there you go, right? And again, here you can put anything from the menu in there. Okay, and here, that's the beauty of it. In JSON schema, it would be much, much more difficult to do. Here, what are we saying here? We have an object that has a key R associated with an array of objects that each have a key foo associated with a Boolean. And this is what you have here, an array of objects, 2 objects with the key foo each, and every time a Boolean. So you see, it's like a template, basically, that applies to the instance. Do we have any question?
Yes. How can we set the min and max?
This can be done. I just didn't want to show it to you because I didn't want to inundate you with too much information. JSON has 2 syntaxes. There is the compact syntax that covers 80% of the cases, and there is a verbose syntax that is a bit more complex that allows you to define subtypes. And in that more verbose syntax, you can say, I'm defining the type, for example, shoe size between this and that size, for example. So this is absolutely possible. It's just something I didn't want to annoy you with. But know that it is possible, that you can absolutely do that if you want, right? Okay. All right. So this is JSON. So we already looked at 2 schema languages, and the 2 schema languages apply to JSON. Now, I also want you to see the same for XML, which is called XML schema. There's actually also others, but we just look into XML schema. Now, I just need to give a word of warning. XML schema is a bit complex. And in fact, that's exactly the reason why every year of the lecture that I'm teaching big data or big data for engineers, I actually reduce and reduce and reduce the size of XML schema and increase the size of JSON. First, because it's increasing in popularity. People like JSON more and more. Second, because it's simpler, right? This is why I'm only exposing you to a bit of XML schema, but do not worry, not too much of it, right? I have to warn you, it's more verbose, but now that you have seen JSON, what it does, you will understand that XML schema is pretty much the same thing, just maybe a bit more verbose. All right, are you ready? Let's go for it. XML schema. Okay, let's go. So this is an XML document. So what sort of things do I want to enforce here? Maybe I want to say, okay, I want my top level element to be foo. It's an element, and I want it to be a string that has text. That's the sort of thing that I could enforce. How do I do it? I do it with this very verbose. I warned you, right, that it's quite verbose. So this is an XML schema. So what's the first thing you notice? XML schema is XML, just like JSON and JSON schema were also JSON, right? We eat our own dog food. That's how it's called. So what do we have in here? We have a schema that defines an element right there that has the name foo and that is of type string, right? So I just copy it over here. So here I have element foo of type string, and this is my instance, element foo with the type that is a string, right? So this is the idea. Now I notice I inverted it compared to JSON. I hope it doesn't confuse you too much. Maybe I should actually swap the top and the bottom here in order to to make sure that, that it's not confusing. So this is the schema and this is the instance. Now, do not be distracted by the paperwork in there. This here is just paperwork. This is just some paperwork that says where the schema is located. So do not be distracted by that, right? Don't focus too much on that. We basically have an element foo that is a string, and we say in the schema it's an element called foo that is a string, and that's it. What do you put in there? That's from the menu I showed earlier, and that's exactly the same as in JSON. Right, so this is also less to learn. You just have this extra prefix here, but again, we've seen that 2 weeks ago, right? The prefixes and the namespaces, so you shouldn't be surprised. Okay, now, okay, so this is just to bind the schema, and you see that's a string and that's a string. So let's change it. Let's say, okay, it's type integer, and here that's an integer. That's fine, right? So here, this is valid against that schema. Now, the menu, I'm just repeating, basically, I've already showed you part of it earlier. This is the menu that you have in XML schema, strings. Don't focus too much on that. This is more advanced. It's a URI. You see decimal, integers, float, double. I told you when we did the generic type system that there is all of that, and it's long, int, short, byte. It's also here. You even have a few more like positive integer, non-negative integer, unsigned long. That just means there is no minus sign in front, and so on. So you see you have a very large menu to pick from, a very large list of types that you can use. You have Booleans, you have the dates, date time, year, month, day. You see there's a very, very long list. Duration, hex binary, that's for the binary format. So you see a very long menu. And by the way, this is the same list as for JSON. Almost all of that can also be used in JSON. Okay. Now, a few examples of how dates look like. So that's both for XML and JSON. In the case of JSON, the dates use dashes. The year, a dash, the month, a dash, the day. When you have date times, you have a T. I don't know why it's a T, but it's a T. You have the date here, a T, and then the time, and Z is just for GMT. It's just that the time zone is 0, maybe. Here, that would basically be Pacific time probably in the winter, right? So this is how you basically can encode. And again, this is just the lexical representation. This is what you would see in the original XML or JSON document. Durations, do not be scared. They start with a P, and then this is 1 year, 2 months, and then the T again to separate the dates from the times, and 3 hours. So 1 year, 2 months, and 3 hours. All right. You can also restrict. So this is what you asked earlier. Can I restrict the types with intervals? Yes, absolutely. Another way you can do it is to say, I want a string, but I want the length of my string to be 3, right? So for example, you can do it for airport codes, if that's an airport, right? ZRH. So you can say with this very verbose and complete, and that's complicated that I give you. But anyway, what we do is the restriction of string by saying the length is 3. And this is how we manage to get that restriction right there. Okay. So here I'm just simplifying everything by removing the paperwork. So you just see really what's essential in there. Right? Length 3, and that's a length of 3. Okay. So this is for the actual text that you can have in there to validate text against an atomic type. You can also validate structures in XML. So how do you do that? Well, you have 4 types of structures that you can see. You can have an empty element, and you want to enforce that it's an empty element. Or you can have simple content, meaning that you have an element and there is some atomic type inside. Or you can have complex content, meaning that you have an element, but inside it's just elements again, right? It's just a list of elements. It's called complex content. Or mixed content. So this is typically if you're a publishing company and you have a scientific paper and you have annotated text, right? So this is mixed content. So how do you do that? Well, you do that also with this extremely verbose and complicated and way of doing that. But basically, what are we doing here? We say, okay, we have this complex type with that I call complex content. It's a sequence of the elements 2 to 4 and 0 to 1. You see, so 2 to 4 and 0 to 1. 2 to 4 is a string, so yes, that's a string. 0 or 1 is a Boolean, yes, that's a Boolean, that's true. And here, min occurs and max occurs. So 2 to 4 must be there between 2 and 4 times, 2 times, 3 times, or 4 times. Well, here we have it 3 times, so that's fine. It's between 2 and 4. And here it's 0 or 1. Well, we have it once, so that's fine. So this is how you can do complex content. Empty content is easy. It's the same thing, but you just don't put anything in there. So it's a sequence with nothing inside, and that gives you the empty element. Remember, when the slash is at the end, it's an empty element. Then we have simple content, but I can still have an attribute. So how do I do that? Again, there's this complex way of saying, okay, it's basically a date, right? So it's a date right there, year, month, day, but it still has an attribute called country associated with the type string, right? I warned you, it's very verbose, it's very complicated, but it just does the job, right? So it does the job of validating. Okay. And mixed content is easy. It's the same as complex content, but you just say mixed equals true, and that allows that text can also appear intermingled with the other children elements. All right? Okay. You can also constrain the types on attributes. So you can have an attribute country that has the type string. So you see country has the type string. And here, that's a question you ask. There's a default here, Switzerland. What does that mean? It means that if the attribute is missing, meaning that imagine that I have this in my instance, what would happen is that the engine that does the validation will automatically add back country equals Switzerland because that's the default in there. So that should also come back to the question you asked earlier about default values. You can absolutely specify a default behavior that if the value is missing, you can just add it. Right? And that's a way also of cleaning up your data. All right. You can name the types if you want to give them names. So this is what we did until now. An element has a certain type, and then you define that type separately. Right? Or you can do it anonymously by nesting the type definition inside the elements. All right. Okay. XML has more. It also supports namespaces, but I didn't want to do that to you. So I didn't talk about how to support namespaces. You don't have to worry about that. We can also define primary keys and so on and so on. And the beauty of XML schema being itself XML is that you can do a self-reference. You can actually validate an XML schema against an XML schema, just like you can validate a JSON schema against a JSON schema. That's called the schema of schemas. Let's say that it's more for computer geeks who want to take it to the next level and who like this form of auto-reference. Okay. Well, XML schema is complicated, right? That I give you, and again, I know that some of you might be scared about everything that I have shown you. But again, as I said, I'm actually downsizing what I show of XML schema in this lecture and insisting more and more and more on JSON, JSON and JSON schema, because I think that this is what is becoming more popular. And in particular, another reason why I do less and less and less of XML schema every year and more of JSON and JSON schema is that when you validate a collection of JSON documents against some schemas, you can actually build beautiful things that are called data frames. Right? So it's basically these denormalized tables that I told you about. It turns out that we can actually draw them in a very visual way. And this is what I will show you right after the break. We'll forget about XML. So you don't have to worry about XML or XML schema anymore for the end of the lecture, just JSON. And I will show you how to build and draw data frames and visualize them in your mind when you have a validated collection of, let's say, 1 billion JSON documents that will look alike. All right, so I will stop here to let you breathe a bit. I even give you 2 more minutes of break, you see, so that you can recover from your emotions after seeing all of that complexity. And I'll see you at 11:10 in order for me to show you the visuals of the data frames. Just as an appetizer, this is the sort of drawings that you can do. But this is something we'll do after the break. So see you in 10 minutes. Thank you.